And by the way, I upload. By the way, I uploaded the recordings last time. Well, today is October 24, 22. Let's take a look at the recordings that I uploaded in my YouTube channel. YouTube. Let's see, YouTube channel. To channel videos. That's 17. 12. Let's see. Yeah, what's missing here is the 19th. I didn't upload the 19th. Okay, so hang in there. So you have every chapter with every recording with the exception of the 19th, which was a lab. That was missing here. Okay. So, and homework for the second exam, right? For the second exam, I want you to study homework 4, 5, 6, and 7. Homework 4 is chapter 3, to the motion. Homework 5 is chapter 4. Homework 6 is chapter 5. Homework 7 was work and energy, chapter 6, what we covered last time. Chapters for the second exam. Here you go. I'm giving you the not chapters, but sections, right? Sections for the second exam. So we didn't cover every section in the book, but that's why I'm, I have listed them here. We're skipping section 4.7. We're skipping section 5.5, and then everything else there in the book. Okay. Any questions before we move forward? I am hoping, let's see, I'm planning to have a quiz today in the last 20 minutes of the class, okay? So plan to be here for the quiz at what, 11:40, right? Yeah, at starting at 11:40 a.m. I'm planning that. It's gonna be like maybe 5 questions, 6 questions, and it's going to be on this material here that we're covering today. So let's talk about that. Chapter 7, right? Momentum. Oh, chapter 7. Let's see. Wait a minute. Chapter 7. Okay, this chapter here. We're going to skip 7.1. Okay, we're going to skip 7.1. I don't like to cover 7.1, but we do cover 7.2, 7.3, 7.4. Okay, maybe 7.5. So let's concentrate on those 3 for now. Okay, so now let me give you an idea what this is all about and how this idea, the question is how this idea of momentum showed up. How did this idea show up? How did this idea of momentum showed up? Okay. How did he come up with this idea of momentum? Okay. I'm going to give a very simple example, and then we are going to elaborate in more examples that are more difficult. Okay. The first hint at the idea of conservation of momentum came up when scientists started looking at the case of an object that was moving with constant velocity. That's the first hint. That's how the idea of momentum starts to develop in the mind of physicists, okay? So if you have an object moving with constant velocity, you know that the net force is 0, okay? It doesn't even have to be no friction, okay? Provided the net force is 0. So look what happens. given instant of time is here, and so on, right? The object is moving with constant velocity. If the object is moving with constant velocity, we can say that the net force is equal to 0. Okay? So let's go ahead. How this idea, we do know, this idea is closely, by the way, this idea is closely associated. This idea is closely related to Newton's first law, to Newton's first law of motion. And then to Newton's third law of motion. Okay. The first hint that there was that the idea of momentum was important came up from Newton's first law. Okay. And by the way, momentum, how is this defined? Momentum is defined, by mass times velocity. That's how we define momentum. And by the way, it's a vector quantity. We represent it by the letter P. Okay, but how did you figure out that was an important idea? Okay, well, we figured out that was an important idea because as the net force applied to the object is 0, its velocity is constant. That's right. So what we can say? We can say that if the net force is equal to 0, the velocity is conserved, right? Remember that idea of conservation, right? So we do know from Newton's first law that if net force is equal to 0, the velocity is constant. Or in other words, the velocity is conserved, right? Initial velocity equal to final velocity. Okay? That's what we say about conservation of any quantity, right? If a given quantity is conserved, the initial value of that quantity is going to be equal to the final value of that quantity. Okay. And then, if you want to be strict about the conservation of velocity, you have to take into account the mass of the particle as well. Okay, so that's how people came up with this idea of momentum. Momentum is mv. Okay, if net force is equal to 0, this quantity is going to conserve. But there's another way too of seeing that. Okay, so if net force is equal to 0, we can guess, right, that the above quantity is going to be conserved as well. Okay, but then there is another way to look at that. There is another. Remember, I said we can guess, right? We are not sure yet. We're just guessing. Is it possible that this quantity here, m times v, is going to be? We do know from Newton's first law that the velocity is going to get conserved. But what if the mass of the object changes as it's moving along, right? So that's why I'm saying we can guess that above quantity is going to be conserved. But then, we refer to Newton's second law, not first law, but second law. Okay? That's how, this reasoning goal. Remember that goals, right? We go. Net force is equal to mass times acceleration. Okay. Compare this equation with this other equation, right? We have mass here and we have mass here. And then we have velocity here. And then we have not velocity, but something else that's related to velocity. It is what? A delta V over delta T. Delta V over delta T. Delta T, okay? Multiply that. Okay. And then we go the next step, you know, and then we go using Newton's second law. We find the following. Find the following. All right. We're using Newton's second law applied to the net force equal to 0. You find the following. Here you go. You know, net force equal to 0. M delta V over delta T is also equal to 0, right? M delta V over delta T is also equal to 0. And what else? Okay, well, delta V is what? It's final velocity. Final velocity minus, oh, it's final, not initial, right? Final velocity minus initial velocity. Here we go. Equal to 0. And what else? We also have that this delta T can be passed to the other side. And finally, we have that M times final velocity is going to be equal to M times initial velocity. So that's where this idea of conservation of momentum comes from. Okay. When you are creating a new quantity, when you are discovering that a new quantity has some special properties, you start with the easiest way, right? You start with Newton's first law, and then as you become more and more familiar with the relation of this new quantity with respect to the first law, you start to elaborate a little bit more on this new quantity, on this new quantity that, by the way, is conserved. Okay. So that's where this idea of conservation of momentum, you know, comes from. And by the way, we have this condition for momentum to be conserved. We must have this condition that the net force is equal to 0. By the way, for momentum to be conserved, we must have this condition that the net force must be equal to 0. the net force is not equal to 0, then momentum is not conserved, okay? If the net force is not equal to 0, then momentum is not conserved. And then you can look at the units of momentum. What are the units of momentum, right? There you go. The unit of momentum is going to be the unit of mass times the unit of velocity. Which, by the way, is kilograms meters per second, right? That's the unit of momentum. And this very simple definition, and not just definition, and property, right, has very important consequences when we solve problems, especially when we are dealing with problems related to collisions. Okay, you're going to see that very soon. So now you can come up with very simple, very simple examples, right? Here you go. What is the momentum of a very large truck, which is at rest, right? Can you come up with an answer to that? Okay. What is the momentum of a, let's say, of a little dog, right? Let's say a Chihuahua, right? Chihuahua. Man, is that how you spell it? Chihuahua. Very little dog. Those dogs that are very small and they walk very fast, right? What's the momentum of a little dog Chihuahua, which moving, let's say, at half meter per second, compared to the momentum of the truck, of the above truck, right? You can start to think about that, right? Which one is going to be larger, right? Momentum depends both on the mass and the velocity, right? Doesn't matter what the mass of the object is, if it's at rest. If this object is at rest, the momentum is going to be 0, no matter how large its mass is. So even for this small little dog, right? Even for this small dog, his momentum is going to be larger than that of a truck, a larger truck. You can think about this type of simple problem. Okay. Okay, so now we should have this, understanding that momentum gets conserved if the net force is equal to 0. Okay. And so conservation, so far we have seen that conservation of momentum is a consequence of the first of Newton's first and second laws. Okay. If the net force applied to the object is 0, velocity is constant. Okay, that there is this first law, Newton's first law has a conservation of momentum implicit in its in the law itself. If you want to know better about momentum, you go into Newton's second law and you find specifically what is the relationship for momentum, right? For this quantity that gets conserved. Okay, so far. However, if we apply Newton's third law, we discover something even more powerful and even more important than what we have discussed so far. Okay, and I'm going to tell you. That's where collisions come into play. That's where collisions and conservation of momentum come into play. So I'm gonna, here you go. I'm gonna give you an idea what's happening here. Now suppose that we have two objects colliding with themselves, okay? The first object, the mass 1. Let's make the simple assumption here that the two objects have the same mass, okay? And let's say also that those two objects, when they collide, they stick to each other. Okay, we're covering this type of example because it's the simplest one that you're going to see when it comes to conservation of momentum and collision. Okay, so here you go. I'm going to play the movie for you. Okay, mass 1 is approaching mass 2. Mass 2 is at rest. Mass 1 has initial velocity 1, v0 They both have the same mass. Is about to collide. Mass 1 is about to collide this mass 2. Okay, I'm playing the movie here for you. When mass 1 collides with mass 2, what's happening? Mass 1 is going to interact with mass 2. There will be a contact force between those two masses. Okay? And by the way, I put a box around mass 1. There's a reason why I put this box around mass 1, okay? I put this box around mass 1 because consider this box around just like your free body diagram. I'm looking only at the forces acting on this mass number 1. That's what they call my system. We have two blocks, and then I'm going to look only at mass 1. When I look only at mass 1, only at the forces that apply to mass 1, what does it mean? It means that mass 1 is my system. Okay? I can define my system whatever way I want. Okay? And so I'm following mass 1. I know that net force between this point and this point on mass 1 is going to be 0, right? And because the net force on mass 1 between this point and this point is 0, then I do know that the momentum of this mass is going to be conserved, right? But can I still apply conservation of momentum after this collision? Yes or no, right? Remember, conservation of momentum applies only if the net force is equal to 0. So at this very moment, I can state that the net force here in the mass 1 is F2 in 1, force of 2 applied to 1, right? And I also know that from the third Newton's law, that the force that mass 2 applies to on mass 1 is equal in magnitude and opposite in direction. Make sense? And after this collision, what's going to happen? Those masses are going to stick with each other. That's what I call a inelastic collision, totally inelastic collision. And the masses are going to move together as they go by, okay? So that's the story that I'm telling you. Okay, so here you go. Consider an object of mass m moving with a constant velocity over a frictionless surface. I'll call that the constant velocity v0 1. Okay. I'm going just to repeat what I did before with that illustration. Okay, over a frictionless surface. Why the net force is equal to 0 on this mass? Why the net force on this mass is equal to 0? The object will continue moving with constant velocity, right? For this reason, we can state that its moment P is conserved. And I'm even going to be more specific. I'm going to say P naught of 1 is equal to PF of 1. Okay. Its moment P1 is conserved. I'm just changing a little bit here the notation. Right? That's the idea of conservation momentum. Moment at the beginning is equal to momentum at the end. Provided the net force applied to my mass or system, I'm introducing this idea of a system, is equal to 0, right? Provided. I can erase that. Now, but then there's the second object that gets in the way. First object is moving towards the second one. The second object is at rest. Before first object collides with second one, net force applied to first object is 0. However, during the collision, the net force is no longer 0. After the collision, the state of motion of both objects change, and the net force applied to the first mass goes back to 0, right? Before collision occurred, we can say the moment was conserved. Moment was conserved for the first object. However, when a force was applied to the first object, momentum no longer got conserved. Okay. So, unfortunately, it seems that we cannot use conservation of momentum in this situation here. It seems, but only it seems. Okay. Right. And that's where the, scientists start to think outside the box. That's where the genius really comes on. Okay. So notice that momentum doesn't get conserved because I am looking at this object as my system. Okay. What if instead of looking at this object as my system, I look at the two blocks as though they were our system? Okay. It would be like a funny object. This system would be like a funny object, an object that compresses, right? That changes its shape, right? Look what happened here. This guy here is moving towards the other guy, right? It's changing its length. It's as though the object is elastic, right? But this configuration, this system, has a very interesting advantage. Maybe some of you have already noticed that. If I consider those two blocks as being a single block, as being a single object, as being a single system, I can come by and say, look, folks, when those two objects collide with each other, the net force in this object is going to be 0 by virtue of Newton's third law. Makes sense? See here, we have this force F21 and F12 applied to our system, to our single block, right? To our system that behaves like a single block. And when I sum those two forces, we get a net force equal to 0. That's the surprising revelation that people every now and then, discover. Okay, and now we can start thinking in terms of conservation of momentum just by redefining our system. Initially, we define our system as being just the first block, but just by redefining our system as being the two blocks, we can state that the net force applied to our system is equal to 0 all the time. And because the net force applied to our system is equal to 0, we can have conservation of momentum. Okay? So that's the realization that someone some time ago came up with. That conservation of momentum applies not only to a single object that are moving with constant velocity, but it also applies to two objects colliding with each other. Okay, so let's do that again. Here you go. Mass 1 going towards mass 2. They interact with one another. Mass 1 applies the force of F1 to mass 2. Mass 2, according to Newton's third law of motion, applies the force of 2-1 in mass 1. But those forces must be equal to 0 because they are equal and opposite to 0. Sum this vectorial force with this other vectorial force, you are going to get net force is equal to 0. So because of that, we can use the law, not the law, but the corollary of conservation of momentum, okay, to this system. Make sense? Okay. So now let's play a little bit with that. And did I convince you of this, on how we can apply this idea of conservation of momentum, right? So that's what I'm describing here. Consider the two masses as being a single object. The mass is our system. The two masses, okay? The two combined masses is our system. In this case, when we have a collision, the net force in this system is going to be equal to 0, will be equal to 0 due to Newton's third law of motion. In this specific situation, because the net force is equal to 0, momentum must be conserved. Must be conserved, right? So here you go. Net force, mass times acceleration, right? Net force is equal to 0, final momentum is equal to initial momentum. Final momentum of my system must be equal to initial momentum of my system. So if we consider the two masses being our system, the final momentum is going to be the final momentum of mass 1 plus the final momentum of mass 2. The initial momentum is going to be initial momentum of mass 1 plus initial momentum of mass 2. Okay. So being a single object, and I also have to say something here. Now consider two masses as being a single object. The two combined masses is our system. Okay, in this case, we have a collision, the so-called inelastic collision, and the two objects stick to each other. Okay. The net force in the system will be 0. The net force in the system will be 0 due to Newton's third law. Again, don't forget, what we have here is what we call an inelastic collision. Okay. So think how we can come up with an inelastic collision, right? That might be a good way of a practical way of generating, right? Visualizing an inelastic collision. Okay. Think, for instance, think of different ways that you can have an inelastic collision. Okay, let's put that aside here, right? think, let's see here. Think of different ways you can come up with an inelastic collision using commercially available products in the market. Okay, so commercially available products in the market. But let's finish solving our problem here. Let's finish solving our problem, right? So here you go, example. Consider two objects of same mass. Okay. First object is at rest. Second object, no, first object is moving with constant velocity V01, and the second object is at rest. And the second object is at rest. Okay, it's moving with a non constant velocity V01, and the second object is at rest. These two objects collide these two objects undergo a totally inelastic collision. Okay, they stick to each other. What's the final velocity of the set? Okay, solution. Okay, let's do that together. Okay, we're going to use this one. Consider two objects of same mass. First object is moving with a constant velocity, and the second object is at rest. A totally inelastic collision. They stick to each other. What's the final velocity of the set? Assume that there is no friction, that there is no friction between the objects and the surface. Okay, let's do that together. And then, like I said, this is the simplest. I'm going to write it down here. This is the simplest type of problem you will see on collisions. Okay? There's the simplest type of problem. You got to understand that. If you don't understand that, you won't be able to move forward. Okay, so you won't be able to do the others. So here you go. We do know they collide with each other. We do know that there is no friction between the objects and the surface that they are moving. Consequently, the final momentum of one must be plus the final momentum of two must be equal to the initial moment of one plus the initial moment of two. Okay. Of course, before that, we have this relation here, which is the momentum of our system, right? Momentum of our system. Okay, final momentum of one, you already know that is going to be given by mass times the final velocity. They have, this mass has the same mass as the other one. Final momentum of two is going to be mass of two times its final velocity, right? And then I can repeat what I have in there on the right side just by exchanging the subscripts right here. Okay. Okay, first simplification, right? First simplification. Simplification. Mass 2 is at rest. What does it mean? It means that VF2 is equal to 0. VF2 is equal to 0. If VF2 is equal to 0, so the second term on the left side, can disappear. 0. First simplification, second simplification, right? What's the second simplification? Because the collision is inelastic, okay? Wait a minute. Oh man, I'm doing what I meant is making this one is not V final is equal to 0, right? Nobody notices that, right? V initial is equal to 0. V final we still do not know, right? Oh man, next time make sure you call, pick that up on that, okay? First simplification, mass of 2 is initially at rest, okay? Correcting here a mistake that I made. Second simplification, because the collision is inelastic, the final velocities of masses 1 and 2 are the same, or VF1 is going to be equal to VF2, or right, VF1 is going to be equal to VF2. I'm going to apply this knowledge right now. Here you go, and I'm gonna call that just VF, okay? To simplify our notation. I'm not gonna call VF1, I'm not call it VF2. What am I asking? What's the final velocity of the set, right? That's what I want to find out. What's the final velocity of the set? So now, here you go. Eliminate that, eliminate that. I don't need the 0 anymore. Okay. This term is equal to this term, so consequently they sum each other. And we are now in a condition to solve the problem, and we don't even need to know what are the masses of the object, because they are the same. So they can not just because they are the same, but because they cancel as well in the equation, right? So here you go. We know what's the initial velocity, and we can find the final velocity from this equation. Here you go. So that's what happens when we have two objects of same mass colliding inelastically. That's what happens to the velocity, to the final velocity of two objects of same mass whenever they collide inelastically. Okay. Their speed and velocities are cut. Their final velocity is going to be half the initial velocity of the first mass. Okay. And then you can repeat the same problem. Then you can repeat the same problem for other conditions. Then you can repeat this same problem for other conditions. Okay. Like, like what? Let me. M1 M1 equal to 2M2, right? What's going to be the final velocity, right? V01 is going to be the initial velocity of 1 is going to be a known value, right? M2, M1 equal to 3M2, and so on. And so on. Okay? That's, like I said, this class of problems that involves inelastic collisions. And by the way, in one dimension, are the easiest problems to solve. Okay. So let's save it here. That's 9:40 right now. Let's take attendance. Okay, so Jade Visquera, are you there?
I'm here.
Thank you. Vanessa Bonilla, are you there? Vanessa, let's see here. Yeah, I don't see Vanessa in my list. So think about this, this type of problems. Let this idea percolate your mind, right? Ashley, are you there, Ashley? I don't see Ashley either. Let's see, Fisher.
I'm here.
Thank you, Fisher. Blessing.
Here.
Okay, Janet Garcia. Hello, Janet. I see Janet here, but I don't hear from her. Okay, I'm gonna put, I start. No, I didn't get to you yet, Lily. Me either. Raymond Garcia. Okay, thank you, Raymond. Lily, okay, now it's your turn, Lily. Can say you're here. Okay, I'll put it one here for you. Okay. And Michael, are you there, Michael? Okay, thank you, Michael. Wendy Hernandez. Wendy is here. I don't see Wendy here. Huh. Okay, Joshua Jimenez, are you there, Joshua? I don't see Joshua either. Ana Lopez, are you there, Ana? Janet Garcia, are you there, Janet? Can you hear me? Okay, Basilio Lopez, are you there, Basilio? I can see Basilio here, but I cannot hear him. I'm gonna put a star here. Next, Vahad. Good, thank you, Vahad. Daisy Mariscal. Okay, thank you, Daisy. Alejandra Marmolejo. Okay, Amarilis Mejia. I see Amarilis here. Thank you, Amarilis. Yesenia Montes Rodriguez. Okay, thank you, Yesenia. Mary Okeke.
I'm here, Professor.
Thank you. Ryan Ong.
I'm here.
Thank you. Artur Pacheco. Okay, Jennifer Perez. Let's see, I don't see Jennifer here. Okay, thank you, Basilio. I don't see Jennifer here. No, I don't see it. Next is Labelud. Thank you. Lydia Rosas Buenrostro. Lydia, I don't see Lydia here. Okay. Donia,
Here.
thank you. Elika Vafei. I don't see Elika. Briana Valencia. Mia Villalobos.
Here, Professor.
Thank you, Mia. Yustena Youssef. Okay, good. So 20, let's see here. Janet, are you there, Janet? Okay, Janet 1, Janet 2. Okay, so let's go for our little break. It's 9:45 right now. Break until 10. Break until 10 a.m. Any questions about that before we go into the break? Okay, yeah, I call you twice, Janet. Okay, let me put here attendance for you. Okay, good. Now we have 21 students. Good. So don't forget, before going to the break, right? The exam is going to be next week on Wednesday. That's November 2nd. Yeah. Let's see, November 2nd. Is that okay? Yeah, we have until 31st. Yeah. Okay, November 2nd. Is that okay if we have exam on Monday instead? What do you think? You know.
Yes. Yes.
Okay?
Monday. Yeah, Monday is fine.
Monday is fine for everybody. I want to make sure it's okay for everybody, no?
Of course.
It's not, no, Lily said no. Okay. Not okay. Okay. So there's just one student that cannot make it. We cannot. Yeah, it would be better. Okay. Wednesday better. Okay. Yeah, let's stick to Wednesday. Give you a little bit more of time, but just remember, right? This material that we are covering, the material that we are covering now between, you know, today and Wednesday is not going to show up in the exam. Okay. Okay. Let's stick to Wednesday. Exam is still set for Wednesday. Okay. So exam. Still exam 2 is still set for Wednesday, November 2nd, 22. Okay, see you in the next 15 minutes. I'm back here. And this one's supposed to be elsewhere. Okay. Now let's look at the. What's this coming? Okay. Nice coffee. Okay. Now let's look at the. Let's look at the energy of the system, right? Of the system whenever two masses collide inelastically. Okay, so let's see what happens to the masses, right? When two objects of equal masses collide inelastically. Okay, so we already know whenever two objects of equal mass collide inelastically, the second mass being at rest. Okay, we already know that the final velocity here of the system, notice that we're talking about the vectors, right? The momentum is a vector. We already know that final velocity of the system is going to be half of the initial velocity of the first mass. So let's look at the initial kinetic energy is given by, right? What's going to be the initial kinetic energy of our system is going to be given by kinetic energy of the first mass, initial kinetic energy of the first mass, plus initial kinetic energy of the second mass. And then we can go ahead and start writing, mass one is equal to mass two, right? We have V01 squared, and then the initial velocity of the second mass is 0. Consequently, its initial kinetic energy is going to be 0. And the initial kinetic energy is just equal to the kinetic energy of the first mass. What about the final kinetic energy? Okay, final kinetic energy of 1, final kinetic energy of 2, final velocity of 1, final velocity of 2, right? Those two velocities are the same. Consequently, what we end up having is mvf1 squared. Okay, I can even go another step here to get it fully, right, documented, right? Final velocity of 2 is equal to final velocity of 1 because we have an inelastic collision. So when those two sum up, it becomes mvf1 squared. And by the way, vf is what? Vf is v naught. I'm going to write that down here. Here you go. V naught 1 divided by 2. Very important. Okay. Here you go. You gotta put this guy is Vf, right? And then you square it and look at the kinetic energy. The kinetic energy of the system becomes 1/4 m v01, which, by the way, is less than the initial kinetic energy, right? Do you see that? So notice that here you go. Final kinetic energy of my system is less than initial kinetic energy of the system. What does it mean? This means that the system loses energy during the collision, okay? So what's happening here? What's happening here exactly? Energy must be conserved. Energy cannot be distract and disappear, okay? So what happened to that difference in kinetic energy that's no longer is our system, okay? That's no longer in kinetic energy anymore. In order the system loses and not loses energy, it loses kinetic energy. Okay, means that the system loses place fields, yeah, kinetic energy during the collision. Okay, so what happened? So what happens to the energy that is no longer kinetic? Okay. Well, it's energy must be conserved. Okay, no matter what. So I can tell you for a fact is that some of the kinetic energy is transformed in energy that is used to bind the two masses, okay? So when the two masses collide and stick to each other, there is some sort of energy here that makes the two becomes together, okay? Stick together to each other. That's one possibility. That's at least that's not one possibility. At least, you know, some of the energy goes to bind the two masses, okay? Another possibility, you know, in addition to that, not another possibility, in addition to that, it's also possible that some of the kinetic energy is used to produce, is converted into sound. Sound has energy too. So when two car crashes, we hear that loud bang, right? That's the dissipation of kinetic energy into some other type of energy. Okay, like in sound energy. Another one should be heat, another possibility. It's a third possibility. Is that some of the kinetic energy goes into heat to warm the bodies of the objects. Okay. So that's what we have for one-dimensional collision. By the way, what's the practical application of that? What's the practical application of that? Okay. Well, we can. There is a practical application for that. Okay. So let me tell you one practical application. Is one practical application is in the determination of the velocities of the car, of two cars that are colliding in the freeway, in the street, okay, or freeway. Police officers, they use the conservation of momentum to find out what's the velocity of one car, to find out if one of the cars were speeding or not, okay? And by the way, today's cars are built in such a way to undergo an inelastic collision. Okay? Which is safer, which is far safer to the occupants of the cars. Okay? So today's cars are built to get themselves wrecked. That's what it is. The wrecking allows the inelastic collision. We say that today's cars are built to become wrecked in a collision. The car gets wrecked, you know, but not the passengers. Okay, it's safer like that. Okay, so that's what we have for 1D collision. For 1D inelastic collision, there is another type of collision that's not exactly a collision. I call that a explosion. Okay. Think about a gun and a bullet. A bullet. They are just like two masses. They stick to each other. Okay, and then through a chemical reaction of the gunpowder, the two objects become separated. Okay, we have this chemical reaction of the gunpowder, and when the gunpowder explodes, the gun exerts a force on the bullet, and the bullet exerts the same force in the opposite direction, right? In the gun. Because the bullet has a mass much smaller than that of the gun, the recoil is not as much because the gun has more inertia. But that's the recoil that everybody sees in the movies, right? If you have, or even if you have handled a gun, every time you fire a gun, there's a recoil on the gun or the rifle as well. So you gotta watch for that, right? So here go, that's the case of, I don't like that. Let me put this guy here to the center. Yeah, better now. And then I'm going to copy and paste. Yeah. Okay, let's see here. Yak. See what about this one? Yeah, that's what I want. Good. I'll copy and paste here. Right? That's what happens. Can erase that, and the two masses move away from each other. I want this one here. Now they're no longer attached to each other, right? Final velocity greater than different of zero. Of zero. Final velocity curve. So here you go. Remember that I told you that the system is one that stretches and contracts, right? In this case, the system is stretching. In the other case, the system is contracting, right? Here you go. We can even play a movie. Here you go. Stretch more, stretch more. Here you go. This mass. One mass moving to the right, the other mass moving to the left. Okay. Here you go. Boom, right? And then the masses move away from each other. Their final velocity is going to depend on their masses. I'm going to take advantage of that as well. If in this case the speeds are going to be the same, but not the velocity, because one mass is going to have a negative velocity, the other one is going to have a positive velocity, like that. Okay, they're initially at rest. At the moment of the forces applied, they start to move away from each other. I don't need that anymore, right? Because I already have those two here. This mass here on the left has a negative velocity. The mass on the right has a positive velocity. But because the two masses are the same, their velocities are going to be the same. as well. And we can even derive that mathematically. I don't need that anymore. I'll put VF. Yeah, you know what? I gotta put minus here. Minus. Okay, play it again. Boom. I don't need that. And oh, we can solve this problem as well. Okay. In addition to inelastic collisions, we also have the opposite of an inelastic collision. I call it explosion. Like the case of a gun and a bullet. Okay? Of a gun and a bullet. Okay, first, so consider that the gunpowder provides a given amount of energy for the system gun/bullet. Right? Assume that the mass of the bullet, assume that a known amount of energy for the system gun bullet, I call it, E. Assume that the mass of the bullet is 20 times less than the mass of the gun. Okay. Fine. The amount of energy of the system, provided known amount of energy, E. But by amount of energy, I mean in terms of kinetic energy. Also assume that the mass of the bullet is 20 times less than the mass of the gun. Find the velocities of the two objects. Okay. Another example. Think about that, how to do it. I'm not going to do that, but think how to do it. Okay. There's this one is a little bit more difficult mathematically. That is, I'm going to formulate another one that's easier. Okay. I'm going to formulate another one that's easier. Try to solve that on your own. Try to solve this problem on your own at home. I'm going to formulate a similar problem, but it's easier to solve mathematically, okay? Consider that the gun, let's see. Let's see. The mass of a gun is 20 times the mass of a bullet. When you fire the gun, you measure a recoil velocity of, let's say, 1 meter per second. Before you stop the gun, right? But just before you stop the gun, just before the gun is fired, the recoil velocity is 1 meter per second. What's the velocity of the bullet? This problem is far easier to solve than the other one. mathematically speaking, okay? So how do we do that? Okay, the way you do it is just referring back to this diagram here. Initial momentum of my system is 0 because both the gun and the bullet are at rest, okay? So we can write that down. Initial momentum, go. And because the net force applied to this system, the bullet plus the gun is 0, momentum, initial momentum is equal to final momentum. And what else? You know, I'm not gonna put 1 meter per second, I'm just gonna put V0 V final one. So I don't have to crunch numbers. See, V final one, I'm gonna put V final one. One is the gun. Okay, so here we go. So initial momentum is 0. And final momentum is going to be final momentum of 1 plus final momentum of 2. Okay. Final momentum of 1 is going to be m the final velocity of 1. Final, here you go, I'm going to put big M, right? Big M, which is the mass of the gun. Small m is the mass of the bullet, the final 2. Okay, so we can apply the knowledge that the mass of the gun is 20 times the mass of the bullet. Oops. Yeah. Okay. We do know what's velocity of 1. Now we have this equation here. We have this equation which turns into something like that. Right? I want to know the final of 2. Notice that we have a change in sign. Okay, and now the m here gets canceled. Right? And the final velocity of, let's see here. And then we get that the final velocity of 2 is 20 times the final velocity of 1. By the way, it's going to be in the opposite direction. Okay, like that. Again, this negative sign states that the one is moving one direction, the other one is moving the other direction. Okay. And by the way, the difference in kinetic energy, you know, is going to be given by the energy provided by the gases, right? By the gunpowder. Note, see that final kinetic energy and initial kinetic energy. Let's see here. Here you go. Initial kinetic energy of the system is going to be 0, right? It's going to be 0 because they're both at rest. Now the final kinetic energy is going to be the final velocity, half of final velocity of 1, big M, V final, right? Half small m, V final 2. Here is going to be 20 times the mass of the bullet. Okay. And let's see, by the way, the final velocity of 2 is going to be 20, 20 times the final velocity of 1. 20 times. This negative sign is going to be canceled because we're squaring it, right? We get what? 20 divided by 2 is going to be 0, 10, not 0, but 10. And here is going to be 400 because 20 squared is 400. Oh, not this one. 400. And that's going to be 200. 210 final result. 210. That's how much energy the gunpowder of this gun provides this system. This is not realistic, okay? Maybe the mass of the bullet. Let's take a look at a realistic value for the mass of a bullet. Let's take a look. Looks like it's more than 20. I consider 20 times the mass of the gun compared to the mass of the bullet. Let's say realistic values for the mass of a bullet and gun. Say a gun of mass 3 kilograms, about 30 grams. So we are talking about more like 300 times. 300 times, 100 times. It's not 20 times. Was being too conservative, right? So guns has masses that 100 times more than the mass of a bullet. Depending on the gun, the mass of a bullet usually range from between 0.0 kilograms and 0.04 kilograms. It doesn't say what's the mass of the gun, but I think you should be, safe, right? If 100 times gun off, let's say 6 kilograms. Okay, yeah, 100 times. See that? So a more realistic value should be 100 times here. So here 100, 100, 100, 100, 100, 100. And then what happens to the kinetic energy of the bullet? The kinetic energy of the bullet is going to be a square of that. The kinetic energy of the bullet is going to be more than the kinetic energy of the gun, right? There you go. 100 here, 100 here, that gets squared. We end up with 50. We end up with 1,000. 1,000. Let's see. 1, 2 more. No, not 1,000. 10,000. 100 squared is 10,000. Okay, here is 50 and 5,000. Here you go. Look at the kinetic energy of the bullet. It's man, it's 100 times more than that of the gun. 5,050. Okay, that's the final energy of the system. $10:33. Let's see. We can go another half hour, right? Who came on board? Let's see. We have 21 students here. Yes, sure. Attendance. Yeah, 21, that's good. So what we did so far? Defined momentum. Okay. Explain where conservation of momentum comes from. Conservation of momentum comes from. Okay. To have conservation of momentum, net force applied to our system must be 0. Look at the collisions. Inelastic collision. Collisions. And what happens to the kinetic energy? Okay. Look at the opposite of inelastic collisions. Okay. In the case with explosions, that I call explosions. In this case, the final kinetic energy is greater than the initial kinetic energy, right? Or in this case, the final kinetic energy is less than the initial kinetic energy. See the difference between explosions and inelastic collisions? Whoa, man, it's getting cold here. Let me get a little bit warmer. Good. Okay, so in an explosion, the final kinetic energy is greater than the initial kinetic energy. Now, what about, are there any other types of collisions? Are there any other types of collision? Yeah, that's the question you gotta ask yourself. 2 collisions, inelastic, totally inelastic, and explosions. Yes, there is another type of collision. Yes, there is another type. It's called totally elastic collisions. Totally elastic collisions. In this case, the final kinetic energy end up being equal to the initial kinetic energy, okay? And that's the one that we're going to study right now. Let's erase what we went to the one dimension. We did that in elastic, one-dimensional inelastic. We can erase that, and then now we're going to do totally elastic kinetic energy. Totally elastic. Here you go. Okay, in the case of a totally inelastic collision, let me show you, let me illustrate how it goes, okay? So here, okay. So again, I'm going to do the simplest example of totally elastic collision, okay? So the first mass comes towards the second one. Here you go. The first mass comes towards the second one. Let me copy this one and paste right here. the second mass is at rest. The masses are the same. Again, that's the simplest type of problem that uses that relates to totally elastic collision. You know, approach the other one, they collide. You still have this pair of forces, action and reaction, and the other one start moving. They don't stick to each other. Okay. Most likely, you have already seen this collision before, you know, in the real life. Most likely, you have seen this type of collision before. If you play pool, and every now and then I see something like that. Okay, you have the balls of the of pool. They have the same mass. Okay, so if you're skilled enough, you can make one ball collide head-on with another one. That would be a one-dimensional collision. And what happens during this process? You know, the first ball collides with the second one. The first ball applies a force on the second, and the second applies a force on the first ball. And then what happens? The final velocity of the first ball is zero, right? Have you ever seen anything like that before in the pool table? Right? Okay. So let's play it again. Here you go. Two masses, they have the same value, the same mass. Two objects have the same masses. One ball is approaching the other one, collides elastically with the second one. The second takes off, and the first comes to rest. That's what we see in the pool table. Okay. Compare that to the case of an inelastic collision, right? We can have an inelastic collision too between the two balls, provided we put Velcro in their surface. Okay, they collide. Let's see. Oh no, I don't want to show that. I don't want to show that. That's I'm gonna show you. Forget about that. Okay, let's just solve this problem now for totally elastic collision. Again, here, what happens with the velocity of the first mass after the collision, right? I already told you that the first mass comes to rest, right? But we can derive that mathematically. Let me show you how we do it. We do have conservation of momentum, but now we have a second condition. We have conservation of kinetic energy as well. Okay? We must have conservation of momentum and conservation of mechanical energy. Because we have this second condition here, it makes this problem more difficult to solve compared to totally inelastic collision. Okay? In a totally inelastic collision, the final velocity of one is equal to the final velocity of two. Not in the case of totally elastic collision. And we also have this condition in kinetic energy is conserved. Because of this situation in which you have both conservation of momentum and conservation of kinetic energy, it makes for a more difficult problem to solve. And I'm going to do that right now. Okay? Here you go, one-dimensional totally elastic collision between two objects of same mass, one at rest, the other moving toward the second one is a known velocity, v naught 1. Find the final velocity of both masses. This is the simple problem in totally elastic collision that you see. It involves two equations. It involves a system of two equations. Okay, so here you go. Initial momentum is going to be initial momentum of 1 plus initial momentum of 2. Final momentum of 1, final momentum of 2, right? Kinetic energy gets conserved. Final kinetic energy of the system is equal to initial kinetic energy of the system. mv naught 1, mv naught 2, mv final 1, mv final 2. mv naught 1 is square divided by 2. Can you do that? Maybe I should do it step by step here. Let me do by, by hand, right? So you can follow more, In the case of in a totally elastic collision, we have conservation of momentum and conservation of kinetic energy simultaneously. Okay? So you go ahead and write it down. Okay, so don't forget the initial, we're dealing with two different objects. So you end up having that the initial momentum is going to be the sum of the separate momenta of the particles. I can copy this one and place it right in here and just change the subscript. And then if I'm lazy enough, I just go ahead and, copy this one at the top, right? And just change the P vector to kinetic energy of 1, initial kinetic energy of 1, initial kinetic energy of 2, final kinetic energy of 1, final kinetic energy of 2. And we got MV01, right? MV02. MV final 1. MV final 2. Okay, you can see that the masses cancel out, right? This problem, like I told you, is more complicated mathematically. Okay, I'm going to see that very soon. Why is that? And let's not forget, compared to totally inelastic collision, this problem is more complicated. It's more complicated, okay? Mathematically speaking only. And now I copy that and paste it here and change the subscripts to final. See, those two conditions must be satisfied simultaneously. It's more complicated from the mathematical point of view, okay? For inelastic collision, you have just one equation that you have to worry about. Here in this case, now you have two equations. So now we can go ahead and cancel out, right? The masses. From the first equation, masses from the first equation gets canceled out. Here too, the half Emma gets canceled out as well, right? And now we have those two equations that involves a square. Oh, and there's one more simplification that we can make. Initial velocity 0, right? Here you go, initial velocity 0. Here go a system of two equations. We want to know VF1 and VF2. That's what we want to know. Okay, so since this is a one-dimensional type of problem, we can, remove the vector symbol from the velocity here. And now we know what we know here. What do we know in this system of equations, right? What are the knowns? What are the knowns and unknowns in the system of equation? What are the knowns and unknowns in the system of equation? Knowns. V01, we know V01. Unknown, VF1 and VF2, right? Okay. Two unknowns, two equations. In principle, we can solve this problem. When we have two unknowns and two equations, in principle, we can solve this problem. Okay, it's just a matter of getting the proper mathematical technique to do that for you. So how do we do that? Okay, one way is for you to eliminate one of the unknowns. Okay, from one of the equations. You can, there are two unknowns here. I'm gonna highlight them. This unknown and this unknown. This unknown and this unknown. Right? So the way to solve this problem is to write one unknown in terms of the other unknown. That's one way of doing that. Erase, erase. Okay, we have here the same. Okay, here you go. So one and then you can choose either to write VF2 in terms of VF1 or choose to write VF1 in terms of VF2. Either way works. I have chosen to write VF2 in terms of VF1. Right in here is V01 minus VF1. Okay. And then what's going to be the next step? The next step would be to substitute VF2 right in here. Okay, and that's what I did. Let's do that. I'm going to do that from scratch. So you follow the derivation, right? So here you go. I'm going to substitute VF2 right in here. Don't forget to square, right? Now notice that my equation now is reduced to a single unknown, right? That's a algebraic technique that we used. I can go ahead and expand this square. Okay, and this guy becomes a plus sign. 2V01, V final one. The square goes up. Oops, I have to put a minus here. And when we do that, the square goes away. Okay. What else? Next step. To the final one. Now we have another the final one here. Okay. Exactly what I did before. Let me just here write in a cleaner fashion. Here we go. Okay. Right? Left of the equation is equal to the right side of the equation. And look what we have. This V naught here, 1, cancel out this V naught here, right? V naught here, cancel out with this other V naught here. And we get a simple quadratic equation. Quadratic equation that's rather easy to solve. I'm going, here we go. 2, I'm going to put 2 in evidence. I'm going to put VF1 in evidence, okay? Okay, oh, here you go. VF1. Here you go. So now we have this quadratic equation that tells us that there are 2 possible solutions for the final velocity. Let me erase that. Okay. Let's go. Here you go. The next step would be to cancel out these two, right? And then we have this solution. First solution is state that the final velocity of 1 is going to be 0. Okay? If final velocity of 1 is equal to 0, the final velocity of 2 can be obtained from the first equation. And the first equation tells us that the final velocity of 2 is going to be the initial velocity of 1. Oh. Okay. Another possibility, that's what this equation is telling us. Another possibility is that the final velocity of 1 is going to be equal to the final velocity of, to the initial velocity of 1. That's another possibility. If we do that and substitute it in the first equation, we find that the final velocity of 2 is equal to 0. Let's analyze those two solutions, okay? Here you go. I'm going to simplify it. First, I'm calling that mathematical solution. First mathematical solution. The first mathematical solution states that the final velocity of 1 is going to be 0, and the final velocity of 2 is going to be equal to the initial velocity of 1. It doesn't have a negative sign there. Second, remember that I used mathematical, right? Remember that I used the word mathematical solution. And the final velocity of 1, the second solution, states otherwise. States that the final velocity of 1 is equal to initial velocity of 1. Which one is the right? Okay, that's the trick about getting the mathematical solutions, right? Sometimes mathematical solutions contradict each other. So you have to choose which one is the correct one. The question is, which one is the correct one? This one or this one here, right? And I'm going to illustrate exactly what does it mean. The first mathematical solution is something like that you saw before. The first mass approach, the second one, they collide. The velocity, the final velocity of 1 becomes 0, and the final velocity of 2 becomes the same velocity of 1. That's what the first mathematical solution is all about. Okay? Let's play the movie again. Here you go. 1, 2, 3, 4, 5, right? The second mathematical solution, let's see what the second mathematical solution says. The second mathematical solution states that the first math approach, the second one, they collide, but the second mass doesn't come for us. The first mass doesn't come to a stop. The second mass somehow passes through the first mass somehow passes through the second mass and continue moving with the initial velocity. That's what the second mathematical solution is telling us. Okay, that's one possible solution for the second mathematical solution. Another possible solution for the second mathematical solution is that the two masses are not in the same line, and they never collide. The first mass just flies by the second mass and continues with its own velocity. Okay, that's what the second solution tells us. The second solution can tell us two different things, right? The second solutions, one thing that the second solution can tell us is that the first mass is just like a ghost and pass through the second one, you know, but since ghosts don't exist, so the only physical possible solution for the second mathematical solution is this one that you see right in here, in which there is no collision whatsoever. Okay. So since we must have a collision, then the only possible physical solution for this problem of ours is the first mathematical solution, right? The first mathematical solution is the physical one. Is the physical one. Is the one that's physically possible. $10.59 right now. Okay, did you get the idea? So now you can go ahead and, like I said, what you see here is the simplest type of mathematical solution that you're going to see for totally elastic collision. Okay, masses are the same, and the second mass is at rest. Then you have all sorts of possible combinations, like mass of one greater than mass of two, mass of one less than mass of two, mass of one and mass of two, they're moving initially, and so on. Okay. So up to this moment, right, we solved only for the cases in which the masses up to this moment the colliding masses are equal, right? Are equal to each other. The problem becomes more difficult when the masses of 1 and 2 are different. But the principle of solution is the same. The principle, the mathematical principles, to solve the problem is still the same. Okay, it just becomes mathematically more difficult to solve them. Okay, that's what we have. It's 11 o'clock right now. Let's go for another break. Okay, and don't forget we're going to have a quiz today. The last 20 minutes of class, and the quiz is going to be for this material that we covered. And the quiz will be for this material we are covering, okay? Let's have our break till 11:15 a.m. Now let's do 11:17 a.m. Do you have any questions before we move forward? Okay, I will save those notes here for you, and I will see you in 15 minutes. I'm back here. $11:20 right now. Okay, I prepared the quiz here for you. It's going to become available at 11:30. And you have 20 minutes to do this quiz. Okay, if you require, okay, 20 minutes for so will be from 11. If you start at 11:30, you finish at 11:50, and then you can go home. Okay. It's 5 questions only on the material that we covered today. Until I put it till 11:59, okay? Let me do the following. I'm going to put it till 12:01 better, 12:01 p.m. So, yeah, let's do it this way. In case you start a little bit late. So we have 9 more minutes to cover the material, okay? And let's take advantage of those 9 minutes that we have here to finish this chapter. So here you go. So we are going to have a quiz today, the last 20 minutes of class, and the quiz will be for this material we're covering today. Okay, it's 20 minutes for the regular students, it's 30 minutes for the special students, okay? Special students gonna have an additional 10 minutes. Special students will have an additional 10 minutes. So what we have, I want to cover in this last 8 minutes, right? 2D collisions. Whether it is, 2D collisions, elastic and inelastic. So what becomes difficult here? Becomes difficult is the quantity of equations. Okay, let me see if I have any slides on 2D collisions here. Oh, okay, I have here. So 2 cars coming at an intersection. Remember that I told you cars today are designed in such a way so they undergo totally inelastic collision. So car of mass 1, car of mass 2, they come at the intersection, they crash with each other, and their motion. Let me see. Okay, here you go. Force of 1 in 2, force of 2 in 1, depending on how the impact is made, right? And then the whole rack traveled, stuck to each other in a given direction until it comes to a stop, right? So that's one way to visualize that. If we are talking about balls, like in the pool table, that's for totally elastic collisions, okay? They are not gonna be, to have a 2-dimensional collision in the pool table, the collision between the balls have to be off center, okay? Instead of head on, they have to be off center. That's why this ball here is a little bit off from the origin. Oh no, I forgot that. Thank you. I'm gonna repeat that. Yeah, don't feel. Yeah, sometimes I forget that, right? So here you go. So let me display here. Okay, we are going to have a quiz today, the last 20 minutes of class, and the quiz will be for this material we are covering today. Special students will have an additional 10 minutes. So what I'm gonna try to cover in the last 6 minutes, right, is 2D collisions, elastic and inelastic. So let's do that again. Okay, here an illustration of an inelastic collision. Okay, one car coming against the other one at the intersection. Okay, like I mentioned before, cars today are designed by engineers so they undergo a totally inelastic collision because that's the safest type of collision that you can experience. In a totally elastic collision, the energy of the collision is transferred to the passengers, whereas in a totally inelastic collision, the energy of the collision is transferred to the frame of the car. So here you go, they undergo this collision right in here. There's this force that each one apply to each other, right? Equal in magnitude, opposite in direction. And then because of the inertia of the two cars, the rack, right? The wreckage takes off at an angle. Okay? Takes off at an angle. And police officers know that. They are taught about that. And they can have an idea of the speeds of the cars during a collision like that, and even distribute fines, right, for the drivers. We come up with an estimate of what the velocity of the cars were before the impact. Here is like I said, this case is an inelastic collision. What about a totally elastic collision? A totally elastic collision, we experience that in the pool table. Okay, so we have one ball of mass m colliding against another ball of mass m that is at rest. Note that the first ball is traveling exactly along the x-axis, but the other one has its center a little bit displaced from the origin. For this reason, the collision is not going to be a head-on collision. It's going to be a glanced collision. When you have a glanced collision, you have a two-dimensional collision. So here you go. This first ball is approaching the second one. Here you go. They collide. Look at the direction of the force. Because this ball is at rest and the impact force is at an angle, this ball will definitely take off along the direction of the force. Okay? Whereas this ball here is going to feel an acceleration contrary to the initial velocity. See, this component of the force is slowing down the ball, but then this component of the force is accelerating the ball in the direction, in the negative y direction. Make sense? Okay, so here you go. So this ball takes off in this direction with a smaller x component of the velocity. Okay, and there. What we do know, and I can derive that for you in a very easy way, what we know about the velocity vectors is that these velocity vectors, they make up a right angle triangle. It's possible to prove that. Okay, it's possible to prove that according to the equations. Okay, according to the equations of conservation of momentum and conservation of energy. When the two masses are equal, we get this result, right? This angle alpha right in here ends up being 90 degrees. Why is that? Because this equation that you see here is that for a right angle triangle, right? The square of the initial velocity of 1 is equal to the square of the final velocity of 1 plus the square of the final velocity of 2. If you compare this equation to the cosine law, you find that this angle here, alpha, is going to be 90 degrees. And what about this equation here? It's a vectorial equation, right? V naught 1 is equal to V final 1 plus V final 2, right? Or V final 2 plus V final 1. V final 2 plus V final 1. This equation shows that we have a right angle, that we have a triangle, a vectorial triangle. And this equation here tells us that the angle between those two velocity vectors is going to be 90 degrees. That's what you have to know about that. Let's see if we have one more thing here. Okay. That's another illustration. Yeah. Good. So we are done with this chapter. You can start the quiz. Right now, the quiz is available, and you can start right now, and I will be able to monitor you folks how you're doing. Okay, I'm going to stop sharing the screen. And I'm going to check. Okay, Raymond started the quiz already. Who else has started the quiz? Remember, you have 20 minutes to do this quiz. The special student has an additional 10 minutes. And the quiz is going to close at 12:01 p.m. Now you already have 40 students doing the quiz. 1, 2, 3, 4. That's good. There's a total of 5 questions. You can plan 4 minutes for each question. Okay, we have 7 students already doing the quiz.
Professor, where can we see the questions?
Oh, yeah, that's right. Thank you. Thank you for reminding me. Man, oh, God. Here you go. I'm going to start sharing the screen with you. Okay, question 1. What's the unit of momentum? Okay, and let me see if I can display question 2 at the same time here as well. Everybody can see that, right? Question 1 was the unit of momentum.
No, Professor, we still can't see the screen.
Oh, not yet? Okay, what about now?
There we go.
Okay, thank you. Sometimes it's tricky to share the screen here in Zoom. Okay, so I'm gonna see 32. You can see those 2 questions, right? When you're ready for the 3rd question, let me know. You know, spend 4 minutes in this one, another 4 minutes in this one, okay? You still see the questions, right? Let's see. Okay, 3 minutes into the quiz. We give an additional 2 minutes to everybody, okay? Because we lost some time. Here you go. Now we should all have an additional 2 minutes to compensate for those 2 minutes that we lost. Let's see, 35, right? Let's go, when we go to 36, I will show you the third question. First question was the unit of momentum, and you have all those options. Second question was the crucial condition for conservation of momentum in a system. This question applies both to the inelastic and elastic collision. 35 minutes, 11:35. Let's wait the clock to turn 11:36. I'll show you the complete options for the third question. Yeah, here you go. Now let's go for question number 3. Let me see if I can zoom out from that. Let me know if it becomes too small for you, right? That sometimes when I zoom out, it becomes too small. Good. Question 3. 2 masses undergo inelastic collision. The mass of the first object strikes the mass of the second. Initial velocity is v01. What's the final velocity of the set after the 2 collide? Here you go. I'll give you a little bit of a space here. Good. When the clock turns 11:40, I will show you the next question. Question 2, question 3, right? Okay, so you should have had enough time to do question number 2. So let's move down. Now we can see question 5. Because when I mean final kinetic energy, I mean after the collision, right? In the initial kinetic energy before the collision. Okay, two students finished the quiz. You can see that two students finished the quiz. That's good. Okay, at this point in time, most of you must be in the fourth question, right? So you have 2 more minutes to go. Most of you has 2 more minutes to go. Okay, if you finish and don't have any questions, you can leave. Okay. It's like everybody finished, right?
Professor, after we submit the quiz, are we allowed to leave?
Yeah, if you submit the quiz, you're allowed. Yeah, if you submit the quiz, you can leave. Yeah, unless you have any questions.
Okay, thank you.
Okay, so everybody is done, right? I'm gonna close this window. Let's see here. Finish. Yeah, everybody's done. Okay, if you don't have any questions, do you have any questions? Okay, so if you're done with the quiz and you want to leave, you can leave, and I'll see you Wednesday, but I'll stay here online for my office hours, okay? Let me stop sharing. I'm going to stop sharing the screen now. Yes.